In the first session of the course, we described the problem of fluid-structure interaction and its equations. We introduced the scaling techniques and performed a first simple dimensional analysis that allowed us to distinguish the cases with and without fluid at rest. In the next two sessions, we will focus on the case of the fluid at rest and will first complete the dimensional analysis performed in the last video. Let's start by presenting again the equations of the fluid structure interaction problem in a schematic form that we will keep throughout the course. We are interested here in the dynamics of a structure described by a single modal motion. All the physical phenomena will be presented on this simple case, and we will deal with the multimode case at the end of the session. The motion of the structure along this mode imposes a velocity at the fluid-solid interface. This defines a boundary condition for the Navier-Stokes equation in the fluid. The latter then exerts a modal force on the structure, which is the projection on the modal motion of the fluid stress at the interface. And finally, a force from the fluid appears in the right of the oscillator equation. Now that we have written the problem in this form, we can ask ourselves about the tools at our disposal to solve this set of equations. If we make no approximation, we have no choice but to solve this set of equations using numerical methods, such as finite element, for example. We can imagine a time increment solution where at each time step, the new position and velocity of the structure are computed by numerical integration, before serving as a new boundary condition for the fluid, which is in turn solved for the new time step. The new fluid stress can then be used to calculate the new modal force. We can then proceed to the next time step, and so on. This type of method is called partitioned. Other methods, sometimes called monolithic, solve all the equations in one step at each time step. These numerical approaches can be very efficient on complex problems, but are very expensive in terms of computing time, and are not always necessary to understand the physics of the underlying phenomena. In this course, we precede the analysis of physics of our problem by a scaling and a linearization of the equations. This will allow us to keep a modal approach throughout the resolution and will facilitate the physical analysis. As a reminder, during the previous video, we introduced two dimensionless numbers. The first one is the reduced velocity, which can be seen as the ratio between the characteristic time of the flow velocity u0 and the characteristic time of the solid dynamics 1 over omega naught. The second number is the displacement number, which is the ratio between the magnitude of the displacement of the solid during its oscillation and its characteristic dimension. From these two numbers, we can construct a new one which expresses the ratio between the characteristic velocity of the solid and the characteristic velocity of the fluid. If this one is large, it means that the fluid can be considered as not being in flow. Consequently, it is no longer relevant to choose u0 as the characteristic velocity for scaling the equations. We must therefore change our choice of characteristic dimensions. In all the studies with fluid at rest, we will use a single characteristic time for the dimensioning, 1 over omega naught. And the characteristic length will always be L in the fluid and the solid. The kinematic condition imposes equality of velocities at the interface between the fluid and the structure. Its scaling now makes omega naught L appear on each side, and dimensionless kinematic condition is simply written as small u equals dxc over dt. In the fluid now. Let's start with the conservation of mass. The dimensionless quantities are shown on the right. This is no different from the choices that were made in the fluid mechanics example from the previous session, except that we choose omega naught L as the characteristic velocity. Finally, this scaling results in a dimensionless number in front of the particle derivative of the pressure, which expresses the ratio of two velocities squared. The dimensioning of momentum conservation does not pose any additional difficulty. Here are the conservation equations in the fluid. We have made appear three dimensionless numbers, which are different from those we have highlighted in fluid mechanics. It is due to a different choice of characteristic velocity. The first number is a compressibility parameter noted K. It can be seen as a special Mach number where the characteristic speed chosen for the fluid is omega naught L. We will see later that it is more relevant to see this number as a ratio of lengths. The second number, Fd, is the dynamic fluid number. Two characteristic frequencies appear, omega naught and square root of G on L. Finally, the third number, called Stokes number, is the equivalent of a Reynolds number in the framework of a structure oscillation at the frequency omega naught. Let us now turn our attention to the scaling of the structural equation. In our description of the dynamics according to a single structure eigenmode, we are dealing with a single oscillator equation forced by the fluid stress at the interface projected on the solid mode. We always use 1 over omega naught and L for time and length scaling respectively. The stress tensor and the pressure are scaled with rho naught omega naught squared L squared. Let us organize the terms and note that omega naught is the characteristic frequency of the solid. It is equal to square root of K on M, which simplifies the equation. We make appear an equation that depends only on one parameter, which is the ratio between the mass of the fluid contained in a volume L cube and the modal mass of the considered mode. This number is called mass ratio. It quantifies the influence of the fluid stress on the dynamics of the solid. Here are all dimensionless equations we have just established. They are represented using the schematic view introduced at the beginning of the video. We see now only 4 independent parameters, plus the displacement number, which is hidden in the kinematic condition. Let's first look at the compressibility parameter. This one can be seen as the ratio of two characteristic times, fluid and solid, but also as the ratio of two lengths, the length L and the wavelength of the acoustic waves emitted by the solid in oscillation at the frequency omega naught. We note in the mass conservation equation that if K squared is very small, we find the condition of incompressibility divergence of U equals 0, which means in this context that the acoustic waves are neglected. Let us look for a moment at this extreme case. What we have just said is that if K squared is very small in front of unity, the vibration of the object does not generate acoustic waves of significant amplitude. We also say that the object does not radiate, and we have shown that this happens when the size is small compared to the corresponding acoustic wavelength. We can easily evidence this phenomenon with a small experiment. Here is a music box mechanism. When we turn the crank, a notch wheel excites small metal blades which enter in vibration. This produces music. The width of the blade is of the order of a millimeter, and the frequencies produced are of the order of a few hundred hertz, say 500 approximately. We find K of the order of 10 to the minus 2, which is very small. We hear something, but the sound seems very weak and very high-pitched. On the other hand, if we couple the music box with a vibrating structure of larger size, we allow the characteristic length of the structure involved in the radiation to be much larger. say of the order of a decimeter. In this case, K is 100 times larger and the sound is much more perceptible. It should be noted that the vibration of the table is barely measurable, certainly of the order of a micron, whereas the blade have the displacement amplitude of the order of a millimeter. It is therefore the characteristic size L that comes into play in the dimensional analysis and not the vibration amplitude. Musicians are familiar with this phenomenon, since this is how they hear the sound of their tuner. It is also partly for this reason that the size of the loudspeaker is related to the frequency range they are asked to reproduce. Now let's look at another number, the Stokes number. This one appears in the momentum balance equation, but it is also hidden in the dynamic condition, written here in projected form on the modal motion of the structure. Indeed, the fluid stress tensor has been scaled using a characteristic dynamic pressure. This gives rise to a term 2 on Stokes as a factor of the strain rate tensor, which is the source of the shear stresses, which are essentially viscous. If the Stokes number is very large, the influence of viscosity will be small in the momentum balance. But our experience in fluid mechanics leads us to be very careful with this. Indeed, we know that the boundary layer's length scale exists. It can have a great influence on the dynamics of the flows, in particular if these boundary layers are subject to detachment. However, we show here that at large Reynolds or Stokes values, the force exerted by the fluid on the structure are dominated by the pressure forces. This is particularly the case in aerodynamics, where wall pressure data is sufficient to quantify the drag and lift force on the objects. The next dimensionless number is the dynamic fluid number. We described it earlier as the ratio of two frequencies. 1 on dynamic fluid squared can also be seen as the ratio of two characteristic pressures. The first is the order of magnitude of hydrostatic pressure variation over the characteristic length L, that is, rho naught GL. The second is the order of magnitude of the dynamic pressure fluctuations in the flow. The inverse of this number quantifies the importance of hydrostatic effects. And finally, the last number is the mass ratio. It appears in the right of the oscillator equation. Expressed in this form, the solid influences the dynamics of the fluid through the kinematic condition, and the fluid exerts a force on the solid through the dynamic condition, which induces a force proportional to the mass ratio. If this number is small, the dynamics of the solid is not influenced by the dynamics of the fluid. It is as if the solid was evolving in vacuum. For example, the dynamics of a structure will not be the same if it is immersed in air or water. The mass ratio will be 1,000 times smaller in air. We have completed the scaling of the problem and have discussed the role of the different parameters. Now we have to linearize these equations and solve the linear dynamics for different configurations depending on the order of magnitude of the different dimensionless parameters.